Chamusha bosses.
Boss, which emotion? What is it? Which emotion? Bosses, so you cancel the record, then like stop recording. Then when the students when you start teaching, you start recording. Yeah, it means ngambocha record the boss apa. Zafunga ku saving of on say by internet with Chimie kama hizo.
Okay, let me stop it.
Yeah. So mkambocha kupunza chepaje. Like before we start teaching now, you can start recording on the cloud.
Okay. Yeah, good morning, everyone. Good morning. Don't know if you can get me. Yeah, so we'll wait for others for about 10 minutes. Then after 10 minutes, we'll start with our lesson for today. Good morning, everyone. We're going to start with our lesson. Yeah, since it's already 10 minutes past, so we're going to start our lesson. Yeah, so before I begin, we're going to pray. Yeah, shall we pray? Our dear Heavenly Father, I come before your sinner. I will come before you as God. Bless me, forgive us our sins, as well forgiven those who have done bad things to us, oh God. Oh God, we thank you for waking us up today until this time, oh God. Oh God, asking you to impact in me knowledge so that I can be able to teach them, oh God, and so that they can be able to understand, oh God. Oh God, as we begin with our lesson, be in our midst, oh God, for we know that if you are not in our midst, nothing is possible, God. Even the possible things become impossible, God. Be with us and protect us, oh God, throughout the lesson. In the name of Jesus we pray. Amen. Yeah, so we're going to start with our lesson. Yeah, I know last time when we started this the amazing topic of Rutherford model, the Rutherford, there's a part which you guys didn't really understand. Yeah, I tried the equation part. I tried explaining my way, and my colleague also tried to go in to also explain in a way which I thought everyone could understand, but we noticed that you couldn't read and understand. So the main essence of this lessons is for you to understand. Yeah, so I'll do a quick recap on the things which we already did. Then, yeah, there's some clarity which I'm supposed to do. Yeah, there's some clarity, and there are some things which I missed out when explaining. So today I'll try to explain it in the most simplest way, so that you guys can get it and you know what we're talking about, because this is the base. And if you get lost on model the Rutherford, yeah, the moment, since we are going like we're uncovering something which is covered, so we're uncovering the atom. We see that Rutherford had a little idea about the atom. Then we see Bohr, the idea increased. Then we see Schrödinger and Broglie, the idea, like they were adding something about an atom. So you have to know the beginning for you to know everything. Yeah. So I thought it is very important for me to explain to you guys. So without wasting any time, we'll do a recap on this. Let's hope you can see my sharing. Yeah. Can you see my sharing?
Yes.
Okay. So today I will do a recap, and I'll do some clarity on things which I saw that there are some errors which I made, or there are some things which you need clarity, and I'll try to explain it in the most simplest way ever. So first we looked at the under this second part, we are looking at the structure electronic des atoms, theories classique and ondulatoire. So we're going to start with it. We started with theories classique. So under theories classique, I said this is simply, I can define it. This is a branch of physics which describes the movement of objects, which must not be greater than the speed of light. So we discussed about that. So we're going to start with model de Rutherford. So a quick recap on model de Rutherford. So we discovered that Rutherford had discovered an atom, and in this atom, he discovered that there was an atom. In this atom, there was a positive charge which was concentrated on the center, and there were electrons which were surrounding the nucleus. So according to Rutherford, he described it as the sun is arranged, as the earth is arranged around the sun. Yeah, that's how he described it. So the problem was, according to theory, according to the theory classique, according to the theory classique, it tells us that when a charged particle is moving around a nucleus, I already explained this, when a charged particle is moving around a nucleus or another charged particle, that charged particle will be losing energy. So when it loses energy, which simply means that it will be losing radiation. When it loses radiation, which simply means that it also loses energy. And when it loses energy, it will simply die. So I'll try to explain all this. Yeah, I did some drawing, and I'll try to explain all this in a drawing which I did for you guys. Yeah, so that you have a wider idea, a wider knowledge about this the thing. You can see my drawing. You can see my sharing.
Yeah.
Yeah, so I did something like I drew something for you guys. So you see that according to Rutherford, he said the nucleus was in between, and the electrons were arranged outside the nucleus. Now these electrons were arranged in such a way that they are not in a definite orbital. If you see here, that's why I've drawn two lines to show the radius. I want you to show that these were not arranged in a definite orbital. Like you see the radius here. The radius here is greater than the radius which is here. So for Rutherford, he just said that these electrons are around the nucleus, and the electrons themselves he didn't know where the same electrons were found. He just said that they're just around the nucleus, but he didn't know where exactly, like the orbit exactly. So that's why you see in his arrangement, they are just like scattered. Here the R is greater, here the R is small. So what was the problem of that? So the problem was we're going to study, like we're going to use the atom of hydrogen. Since atom of hydrogen is very simple to start, and it has only one electron. So assume an atom of hydrogen. This is an atom of hydrogen, and this atom of hydrogen is moving around the nucleus, not in a what? Not in a fixed orbital. It is moving around the nucleus, not in a fixed orbital. So for him, he said this electron, it is moving as the Earth moves around the sun, as I explained. Now, you know that Earth is matter, and matter is not a charged particle, and matter doesn't lose any energy when it's moving. So there will be no loss of energy of the Earth. But here we're dealing with an electron which has a charged particle, an electron which has a charged particle, which means that if this electron is moving in a uniform circular, but not in a stationary orbit, when it is moving, each time it's moving around the nucleus, it is radiating some energy. And when it radiates some energy, so here it radiates some energy, it loses some energy. When it loses some energy, you will see that this R will start, the R here, the R here is big than here. So this R will start what? Reducing. Like its energy will start reducing. So when the energy reduces, then the electron, the distance between the electron and the nucleus will start reducing. So you see here, it's moving, it's reducing, it's reducing, it's reducing, it's reducing until it hits the what? The nucleus. So we see that since when an electron is moving around the nucleus, it's losing energy and it's reducing. And when it is reducing, it will definitely at some point hit the nucleus, and the electron will be destroyed, or the atom in general will be destroyed. That's according to Rutherford. I want you to get me clear. So here the point which you are supposed to get is that one, Rutherford described electrons around the nucleus, but these electrons are not arranged in a fixed or stationary orbital. And two, he described the movement of these electrons as the Earth moves around the sun. But the Earth is matter, meaning it doesn't lose any energy, but the Earth is matter, it doesn't lose any energy, but an electron is a charge. And we know that according to the theories which we learned last time, we know that when a charge is moving around another charged particle, it radiates somewhat energy, which means it will be reducing in energy, and the distance between the nucleus and the electron will be reducing until it hits the nucleus and it is destroyed, and the atom in general is destroyed. So that's the nutshell about Rutherford. That's just in a nutshell. I've explained that in a nutshell. So this one you should put it in mind, because when you go to Bohr, I want you to connect these the things which I've said. Yeah, I want you to connect the things which I've said when you go to Bohr. So now let's deal with the calculation of energy total. So how did he calculate energy total? So these really are things which are simple. You know that when an electron is losing radiation, and when an electron is moving, when an electron is moving, you know that. So you know that when an electron is moving, there is potential energy and the kinetic energy, because energy, as you know, energy is not lost, but it's transformed from one form to another. So it's transformed from kinetic energy to potential energy. So where always if you want to calculate total energy of a moving particle, you should always put in mind that there must be kinetic energies. If someone has a question or what? There must be kinetic energy and the potential energy. So that's what you should always put in mind. So this is kinetic energy, this is potential energy. So you can simply represent it into energy cinetic. This is kinetic energy, just the same energy cinetic plus energy potential. So the first thing is we're going to search for the V, the energy potential. We're going to search for the energy potential according to our atom. Remember that we are using hydrogen because it's simple to calculate and simple to use. So let's find our energy potential. So when you want to find our energy potential, this is our atom. You see our atom. That's our atom, and we've got a nucleus and an electron here. So you should see that there's a line here which represents the attraction force between the nucleus and between the electron and the nucleus. And if you see here, there's also a line which is compensating it, which is what? Force of centrifugal. This is the force which is compensating and which is making an electron to move. Then this shows the direction of an electron which is moving at a certain velocity. So how do you calculate your potential energy? You know that as an electron is moving around the nucleus, the dV, the differentiation or the variation of, there will be variation of potential energy in such a way that you see the R will be always changing, meaning the R will be varying, and this differentiation is dependent on the force of attraction, and is dependent on the force of attraction and the R, which is also always in varying. Yeah, so we see that there's a force of attraction. So you see when an electron is moving around the nucleus, you see that the R will always be changing, and the force of attraction, if the R is changing, the force of attraction changes, and if the force of attraction changes, the potential energy will definitely change. So how do you calculate? So it will be dV is equal to S integral R infinity module of force attraction times, this means times, when I put the point, times dr, which is in constant change. So how do you calculate your potential energy? So the first thing, when you want to calculate your potential energy, you have to know your force of attraction. So how do you know your force of attraction? So under the force of attraction, the attraction is between it is between an electron and a nucleus. So an electron is denoted by a negative charge. This is a charge. This simply means a charge. Then a nucleus is denoted by a positive charge. So this is a charge for a nucleus. Yeah. So how do you find it? So here you say force of attraction is equal to the charge of an electron times the charge of a nucleus over 4 pi epsilon R2, which is the R, which is always in changing. So when you do your multiplication, when you apply here on top, Hello, can you get me now?
Yeah, we can get you.
Yeah,
Yes.
there was a problem. I don't know what happened. Like I was disconnected. So, yeah. So we'll continue. I don't know if from there you are following. From where? So, yeah. So this is so simply. So when you multiply, yeah. So when you multiply the charge of an electron times the charge of an ion, it will give you negative E2 over 4 pi epsilon R2. So 4 pi epsilon, this is always a constant, which is always given. Then R2 is the radius, which is which is varying. Then the negative E2, this is simply the charge. So now how after after knowing, there's someone who has raised his hand, you can ask your question. I think it was a mistake.
I
Yeah,
have a
so-
question. So I said we use this formula when what is force of attraction is changing, or when do we use this formula?
The same formula.
Yes.
This formula is used you know when force of attraction is applied, not really when force of attraction is changing, but when there's a force of attraction which is applied between an object, a negative object and a positive object. This formula is always used. And you see that when you go to Bohr, the electron, the electron was moving in I'll explain more about Bohr, but the electron was moving in a stationary orbit, and which means that if it is a stationary orbit, it means that the R is always the same. So what I can say is that this formula is used where there's an attraction between a nucleus and an electron. I don't know if it's clear.
Yes, it's clear, I think.
Yeah, so now, so after finding our FA is equal to negative E squared over 4 pi epsilon R2. That's our FA. So according to Varinov, our DV, now we're going to calculate our DV. We're going to integrate our DV. We're just going to, after we found this is our force of attraction, after we found it to be this one, we're just going to replace it here. Then we'll try to calculate our potential energy. Yeah, so HK, you had the question, you can ask your question. I saw your hand.
So was saying there's a force of attraction between an electron and the nucleus, isn't it?
Yeah, there's a force of attraction.
So what's causing the force of attraction between the nucleus and the electron?
Okay, that's really a nice question. So the thing which is causing force of attraction is, as you learned in secondary, if you have two charges which are opposite, you have a negative and a positive charge, they will attract. And if I have two charges which are of the same, if I've got two same charges which are not opposite, let me say positive and positive, they repel. So when you see an electron is negatively charged and the nucleus is positively charged, I've even put it here. So that's why there is this attraction. I don't know if it's clear, the force of attraction.
So is it possible to have a nucleus that is positively charged, or it's always neutral?
What?
Is it possible to have a nucleus that is positively charged, or maybe it's always neutral?
A nucleus actually is never always neutral. A nucleus is positively charged. An atom in general is the one which is neutral. What I mean is that the number of protons is always equal to the number of electrons, which means that if the number of protons are equal to the number of electrons, if the positive and the negative are equal, they'll cancel each other and they'll make an atom in general to be neutral. So the nucleus always is positive.
Okay, thank you.
Yeah. Since neutrons, we saw that the charge of a neutron, so a nucleus is made of protons and neutrons, and we saw that the charge of a neutron is 0. So the nucleus takes the charge of a proton, which is positive. So I think from there you are fed.
Yes, thank you.
So continue with our equation. So we know that integral. So now we just replace our FA, which we have found, into our first equation here. So FA here. So you know, I think you learned in analysis with NST or in algebra with ESAW, I think you learned that if you get a negative number, this is a negative E2, when you put it in a modulus, it always becomes a positive number. So don't get confused when I write positive here. Say, where has the negative gone? So when you get a number and when you get anything which is negative and you put it in a modulus, it will give you a positive. But when you get a positive, if it was already a positive, I put it in a modulus, it will still remain a positive. So it only changes when I get a negative. That's when it will become a positive. So I'll just put it here the FA, since it is a module, times dr. Yeah. So now we'll start now the calculation. Yeah. Just follow me the calculation on how we derive our V. So we say V is equal to, we know that E2 4 by E0, this is always a constant. You should always bear in mind that this is always what? A constant. This one, you cannot integrate it, is a constant. So you just put it aside, then we are only going to integrate it, the one which is this side. So we're going to work with this one. Then after we find the answer for this one, we're just going to multiply it with this one. So how do we integrate this one? So when we're coming to integrate this one is just the same as integral r infinity 1 over r2 dr, which is also the same as integral r infinite r negative 2, you know, dr, which is the same. If we integrate it, we just add by 1, then we divide, we also add by 1, then you have r negative 1 over negative, which will have negative r negative, which will give us, if we bring r down here to be negative 1 over r, then r to infinity. You know how to do with this one. So this one is, well, first we're going to put r inside, so it will be negative 1 over r minus, after that we'll put infinity inside, 1 over infinity. And you know that you should always know that 1 over infinity is always 0. The answer is always 0, 1 over infinity. So if it is 0, meaning it will be negative 1 over r minus 0, which will give us is equal to negative 1 over r. So you have found this part here, which is negative 1 over r. So after finding this part here, what you do simply is your V will be equals to the part here times negative 1 over r, which will give us negative E2 over 4 by E0 r. This is the potential energy which you are supposed to get, as simple as that. So here you should notice that we want to calculate energy in putting in mind that when putting in mind the charge of an atom, or in putting in mind the charge of an atom. So here it's all about calculating energy total in putting in mind the charge of an atom. And here, this formula gives us the charge of an atom, which is negative E squared over 4 pi E0 r. So r is the radius between an electron and nucleus. This is always a constant. Then E2 is the charge of an electron. I don't know if I'm clear on that, on finding potential energy.
Question. How did you come up with the infinity as our lower limit?
The infinity.
Question.
So the infinite as our lower limit, how did I come about it?
Yeah.
So you know that you learned about ionization. No, in secondary, I don't think you should learn about ionization. But what you should know that, in simpler terms, I can say, when I get calcium, for example, when I get calcium, for example, an atom of calcium, what usually happens for an atom of calcium is that when I want to turn it into an ion, it will lose electrons, and these electrons will move into, like, when it loses those electrons will move away from the atom to a place where I don't know, to a place which is infinity. Which, that's why I say infinity. You cannot really know where the radius of a nucleus and an electron is sometimes when an electron is lost. So an electron can be found at an infinity. It's possible to find an electron at an infinity in such a way that when you lose an electron goes somewhere where I don't know. The radius is very big, where you just put infinity. Yeah, I don't know if it's clear. That's why they said you can start from R. The electron can be found starting from R, going to the infinity. The infinity, just the larger number. I don't know if you understand.
Yeah, it's clear.
So I don't know if it's clear about. I see there are some questions here. So
can we use an example of another atom?
for this one, they basically use hydrogen atom, because hydrogen atom is easy to play with, and it's easy to calculate. And you see that this formula, when you go forward, this formula will not be applied on atoms with a lot of electrons or a lot of shells. It won't be applied. So you see, so here actually is just the same as if we are studying about hydrogen. So here you're just studying for hydrogen. For other atoms, I'll give you when you go when you advance in learning, I'll give you for other atoms, like how can you calculate the energy for something which has a lot of electron shells and a lot of shells and a lot of electrons. Yeah, is it clear? So
Yes,
this,
thank you.
yeah, so this one only applies for hydrogen atoms or atoms with one electron in the shell.
So does that mean for other atoms use a different method, or
What?
does that mean we use a different method for other atoms?
The what?
Does it mean that we have to use a different method for other atoms?
Yeah, you have to use a different method. Like you have to use there will be a different method of finding energy, which I will teach you also. Yeah, there will be different formula, different method of finding energy. It's not the same.
Okay.
So this one is, huh?
Okay, so how many atoms altogether can use this formula?
So this formula, there's no result. This formula
Yeah.
is mostly used on hydrogenoid. We will learn about hydrogenoid. Hydrogenoid, this is an atom which has lost almost all its electrons, and it has only left with one electron in its shell. It has lost all electrons, it has remained with one electron. You can use this formula. So this one, it's used on hydrogenoid, and yeah, that's for hydrogenoid.
So just
Other atoms which are hydrogenoid.
okay.
So you will learn about that also in this. Yeah. So now we have found the potential energy. So after finding the potential energy, yeah, after finding the potential energy, now we search for the kinetic energy. So I found the potential energy, which is negative E2 over 4 pi epsilon r. Yeah, we'll now go to search for kinetic energy, which is kinetic energy. So the main instance is for me to find energy in terms of a charge. And you know that our kinetic energy is 1 over 2 mv squared, where there is no a charge. So how can I bring about a charge, and how can I bring about for unit of the equation? So we'll look about that. Yeah, we'll look about that right now. Yeah, and before we look about that, Daddy wants to add something. Was saying wants to comment something. You can add.
Yeah, as in good morning, you guys. Just in addition to, I don't know who asked that question about the lower bound being positive infinity. So the idea is the reason why you are including positive infinity is because, like he explained, with principle de Bohr, you are using the hydrogen atom as your reference. So for now, you're using hydrogen as your reference. Even when you start doing hydrogen, you'll be using hydrogen because it's the simplest you would have, and it's the only atom with one electron. Then when you apply it on an atom with one electron, it's possible that you're going to apply it. It's going to suit on atoms with more electrons. So the reason why you add positive infinity is because when you guys learn about what do you call it? When you learn about the series, like when the hydrogen atom was exposed to light, it formed different types of series that you guys call electromagnetic waves. That you call série de Lyman, série de Balmer, série Paschen, etc. So as the series increase, the quantum numbers increase as well. So it means the radius is also increasing relative to the nucleus. So like Jacob is going to explain, you have got the first orbit to the second orbit to the third, Juscala n is equals to positive infinity. So this is where the positive infinity comes in, because right now we're only solving for hydrogen. Hydrogen only has one shell. So for elements that have got n shells, like we don't know where they reach. Take for instance, you have an element like xenon. Xenon is somewhere like a number. It's in period 4 of the periodic table. So you find that the number of shells is high. So for us to calculate with reference to hydrogen, we are going to say the limit should go to R and the limit should go to positive infinity, because we're using hydrogen as reference. Then we're also taking into consideration other elements that are not hydrogen atoms. Yeah. So I hope it's clear, because for now, with principle de Bohr, you're only using hydrogen to be your reference. So whatever you're going to use on hydrogen should be a basis on all these other elements. Take it B calcium, B sodium, B magnesium, B the what do you call it? The group 8 elements. Yeah, hydrogen is a reference. When it comes to hydrogenoids, it's the same thing. You're going to use hydrogen as a reference to other hydrogenoids, because hydrogenoids are atoms that only have one electron. So calcium loses all its 19 electrons and only remains with one. So if it loses all the 19 and remains with one, it becomes a hydrogenoid. So you apply the same principle that you applied on the hydrogen atom to apply on the calcium hydrogenoid. I hope it's clear. So the positive infinity is only used to show that there are atoms that are different from hydrogen that have got many shells. So for us to calculate to also account for those ones, we're going to say it goes to positive infinity. But in a sense where we know the lower bound and the upper bound, we are going to put them. But now, because this is just a generalization, like we're just deriving a formula here. The formula that we're going to derive is what we're going to use. This whole thing here is just to show you how things come about, how principles are being applied and all those things. Yeah, thank you very much.
Yeah, thank you, Mr. Daddy. So Veka, yeah, like explains when two heads are put together, information like you guys want you guys to have a lot of information, and yeah, because when you go to university, you have small tools, and it's really difficult to go into deep into these things. You just do the upper part, you study, because you have a lot of things to study. Yeah, but actually, when you go to universities, but mostly things which comes are things which are in your polycopy and things which they are giving you. So you do your TD, you study your polycopy, and yeah, you do exercises, you study your polycopy, and you'll be able to validate the whole semester. It's not difficult. People have done it, you can do it. So we'll continue now. Now, after we found our potential energy. Yeah, this is our potential energy, which is negative V squared over 4 pi epsilon 0 r. So now we're going to search for synthetic energy or kinetic energy. So they've given this formula of kinetic energy. So now, why can't I use this formula as a kinetic energy? Because I'm dealing with an atom which has got a charge. And so if I'm dealing with an atom which has got a charge, I need to change this kinetic energy in such a way that a charge must appear in this kinetic energy. And if I'm able to search for a nice formula which will have a charge in it, I'll be able to calculate the total energy properly. So how do I do this, or how do I look for the kinetic energy? How do I look for the kinetic energy at which this electron is moving? So you know that according to the formula, kinetic energy is equal to 1 over 2 mass of an electron V squared, whereas is force of centrifugal. Force of centrifugal, this is simply, when I say force of centrifugal, don't get confused. When I say force of centrifugal, this is simply means this is the force which is here, the force which is compensating. There's a force of attraction. The force which is compensating is a force of centrifugal, which is making an electron to move at a certain velocity. So what is this formula for? The formula for the force of centrifugation. So the formula for force of centrifugation is mass of an electron over mass of an electron, the velocity over radius. So this is mass times velocity over radius. So the mass of an electron, the velocity which it is moving about, and divided by its radius. That's the formula of force of centrifugal. So how do you calculate now? Now, how do you calculate energy kinetic? How do you find this energy kinetic which we are looking for, which must have a charge inside it? So how do you find it? So according to the second law of the Newton, it says if a particle is moving in equilibrium, when a particle is moving in an equilibrium around a nucleus, the force of attraction must be equal to the force of what? Centrifugal. So when this particle, for the particle to move around the nucleus, you have to have the balances in forces. The force of attraction must be equal to the force of what? Centrifugal. So now, knowing this in mind, that the force of attraction, that's why I've seen the magnitude is just the same, the distance and the distance here just the same. So I made sure that I read the distance, they are similar, so that you see that if you have to apply the same force of centrifugal, the same force of attraction must be compensated by the same force of centrifugal. If you know this, I know my force of attraction. My force of attraction is E squared over 4 pi E 0 R2, which we have already found. Then FC, which I've already given you, is MA V squared R. That's our FC. So how do you calculate now? So the first thing is the R here will cancel and the R here will cancel. So we have E squared 4 divided by 4 pi epsilon R, which will just remain R, is equal to MA V squared. Since the R will go, so V squared. So how do you go about now? So now we will make it V squared the subject of the what? Formula. So when you make V squared the subject of the formula, it will be V squared is equal to E squared over 4 pi epsilon R MA. So you have made V squared the subject of the formula. And if you are seeing what I'm seeing here, you know your formula for NH-scatic. Your formula for NH-scatic is 1/2 mass of an electron V squared. And the V squared you have found is this one. So here your main aim is just to replace where there's V squared with this here. I hope you are following me. So after replacing, we'll replace where there's V squared. We'll replace, this is our formula here. After we replace, then after replacing, we just multiply. After we multiply it to give us MA squared 8 pi is epsilon R ME. So ME and ME will cancel out, so we will only have E squared, which we have. And this will be E squared over 8 by epsilon R. This is the NH-scatic. So you have known the potential NH and the NH-scatic. So we have known our potential NH and our NH-scatic. Do you know that NH total is NH-scatic plus potential NH? So our potential NH is this one, which we'll write here, E squared over 8 by E0R minus our potential energy. Our potential energy is this one, which you found. Yeah, I think you followed how we found it. Then is equal to, we just factorize. We know that we have got same variables. There's pi, there's epsilon R, there's so just what factorize it. After factorizing it, you have E2 over 4 pi epsilon R in brackets to have 1/2, which is just the same of 1, which will give us 8. This 1/2 minus this one, this is just the same, it will be -1, which will give us is equal to E squared over 4 pi epsilon R negative 1/2. Yeah, negative 1/2. So when we multiply this, it will give us negative E squared over 8 pi epsilon R, which will be NH, which is the NH total. So donc the NH total will give us negative E squared 8 pi epsilon R. This will be our NH total. I don't know if it's clear from there.
It's clear.
Is it clear? Or yeah, so here, like here, what you should only know is the NH total. You just have to know it by heart. They will never tell you what derive for us the NH total. No, you just have to know the NH total by heart. And also, you have to know the NH potential by heart, because these two we use them in a formula of Bohr. We see when you go to Bohr, you use them. So you have to know them by heart. You just have to know the most important thing, know the end results, how they are coming out. Yeah. So yeah, so this one you are now clear. So here we are just calculating the NH total of an electron which is moving around the nucleus, and we have developed a formula which we'll be using. Yeah, so you see that this formula, actually there are slim chances that they'll give you a question to use this formula, like you to use this formula. There are slim chances, but this formula is just a backbone for us to discover a formula which we'll be using most in our questions, which I'll give you. If God allows, to have to finish today with this chapter. Yeah, if God allows. So now we have known how to. You can ask your question.
Everything I've understood, but I just want to take you back on the potential energy formula, where we're solving on how to come up with it. Can you take
potential energy?
The potential energy formula, then how we're coming up with it. I mean, I want to ask a question on that part.
No, okay, I'm coming. Yeah, I see. You can see it.
Oh, okay. Yes. Just on the first part there was that that's the negative E times the E. Sorry, but I didn't get where those where the negative E multiplied by the E were coming from.
Okay. So as I said earlier, I said that you have seen this is there's an electron and a nucleus. So E is simply a charge, and you know that a charge of an electron is negative. That's what I say, negative E, and the charge of a nucleus is what? Positive. That's what I'm saying, E. So for me to calculate the attraction which is between the two charges, the force of attraction, I just multiply the two charges, which is negative E. This is the charge of an electron times E, which is the nucleus, which is positive. Then I'll have negative E squared. And I said divided by 4 pi epsilon r squared, where 4 pi epsilon is a constant and r squared is a what? It's a radius between the nucleus and the electron. And when I put it in this equation, we see that here, when you see these two lines here, it means it's a modulus. And a modulus of anything, a modulus of any number, it's always positive. If it's positive, it remains positive. If it is negative, it has to change to positive. I think you learned about this in algebra or analysis, one of these, I think you learned. Yeah, so that's all. I hope it's clear.
Yes, it's understood.
Okay. So now, now I've known how to calculate the energy total. So so I've known to calculate the energy total. So return to our notes. So here simply I was trying to calculate, so I've done all this. So there's this part which I want to explain, this part. So the first part is just saying that relation qui permettant d'exprimer it soit en fonction du rayon de orbite, soit en fonction de la vitesse de l'électron. So here just saying that energy total is what is expressed in function of the radius and in function of the vitesse. In function of the radius in such a way that the radius is changing, potential is just the same as potential energy, and in function of the vitesse, which is the kinetic energy. So this one you shouldn't stress much. Now we come to the most interesting part. Or in French, it can mean now. Yeah, in French, or it means now. So now there was a problem which was supposed to be overseen, because we know that the atom of hydrogen is stable. The atom of hydrogen is stable. In simple terms, I can say all atoms are stable, because if atoms were not stable, I'm saying in general, all atoms are stable. If atoms were not stable, we know that as human beings are made of matter, would have been destroyed. Even we see things like the things in the space, a lot of things in the space are made of matter, they have been destroyed. If we followed the formula of Rutherford, which is electron is using what? Is using energy, and an atom is destroyed at last. So we see the formula of Rutherford had a problem somewhere, because we know that atoms in general, they are never destroyed. Atoms in general, like here I'm matter, I'm growing, I'm what? You have never seen a person being destroyed, then you say an electron has been destroyed. No. So we see that we have never seen an electron being destroyed. So we see the limitation of Rutherford thinking, or the limitation of how Rutherford in his time thought, his thinking. And the other problem was that for Rutherford, we see that Rutherford thought that when an electron is radiating some radiations, it only radiates what? One color. But he was startled, or he was surprised when he saw that there was the spectrum, they mentioned the hydrogen, spectrum, the red. When he saw that hydrogen could emit actually a lot of rays, like a lot of rays of different color, of the distinct energy of, like, he was surprised. He couldn't really explain why the rays were like, why these different rays, why these different things. So I want to build on from here. We are going to start under our modern day Bohr. I want to build it on from here. So Bohr had a task to do in such a way that this young man Bohr had a task to do in such a way that he has to prove that an atom is stable. You can't destroy an electron. For him to save the same chemistry which we have, he has to make sure that he be able to defend that an electron actually doesn't lose an energy and it doesn't get destroyed, and an atom doesn't get destroyed. And he has also to improve that there must be spectra, the spectra of emission. He has also to improve that the spectra of emission and these spectra of emission are for this and this reason. So we will see Bohr explaining these things, and you will see him opening our eyes according to this thing. So here is about it. We have seen the little knowledge of Rutherford, which had a bit of problem. Now we'll see the little knowledge of Bohr. Yeah, and after we see the little knowledge of Bohr, we see that he also made the mistake. You know, human beings are limited. We don't know everything in general. So now we're going to the model of Bohr. So according to the model of Bohr, I think I showed you an experiment. So Bohr, what he did, he got hydrogen gas according to the experiment, which he got hydrogen gas, and he had put it inside something like a closed, I can say a closed container or closed vessel. Yeah, he made something like a circuit. Then in that circuit, he directed some charge in that form of a closed thing which contained hydrogen. And what happened was he observed some spectra of what? Spectra of emission. So when he observed this spectra of emission, Bohr developed something like a postulate. A postulate is reasoning. You see something, you reason, maybe reasoning in such a way that you assume that because I've seen this, I think it's because of this and this and this and this. So he developed a postulate. So when you hear the word of a postulate, it's simply an assumption, things which are not real, but you just assume they might have happened. So he assumed. So what did he assume? So he assumed this after he had directed that charge into something which is like a closed thing which contained hydrogen gas. He discovered that there are spectra of emission, and this spectra of emission had a definite what? A definite energy or a fixed energy in such a way that if one spectra, for example, if one spectra is 2 joules, the other one will be 3 joules, like it will be, the energy is always constant. We discovered that this spectra had a definite what? Energy, which made him to think that if this spectra have got this definite energy, meaning we have got some orbitals or we have got some what? Shells. He brought a theory, or he brought an idea of shells. So we see that Rutherford, for him at first, he never even knew that there are shells. For him, we just say that the electrons are just, we just put it as in electrons are just, they are moving around a nucleus. That's how he had put it. And we don't know, they're just scattered around the nucleus. That's what I'm saying. That's why I said that first when I was beginning, with this event, the radius of the electrons were toujours different, were always different. So here we see Bohr, for him, he developed a theory of shells. He developed something called shells. So we'll see this postulate in a clear view now. We'll see this postulate. So he developed some postulate which I'll pass through and I'll explain. So under Bohr, I'll make there's some clarity which I want to do here. I made some mistakes. Yeah, under Bohr, I made some, when I was explaining, I had mixed up some information. So I'll do some clarity here. So how do you go about it? So we see that le modèle de Rutherford ne permet pas d'interpréter le spectre d'émission de l'atome d'hydrogène. So we see that the atom of Rutherford does not permit the interpretation of the emission of spectrum of hydrogen. Bohr a été donc amené à améliorer ces modules planétaires et à formuler un certain nombre de postulates. So Bohr, he took it upon himself to make this model of this big man by the name of Rutherford, make it better. He took it upon himself to make it better. So to make it better, he developed some formula which are called, he developed some number of postulates. The postulate, I said, don't be confused about this word, it's just a simple word, an assumption. So c'est le modèle atomique de Bohr. So we're going to look at the model. This is the model of atomic de Bohr. So we're going to look about at it. So how did Bohr describe this the arrangement of the nucleus, the electrons, the shells? How did he describe it in his postulate, in his assumption, in his reasoning? We'll see how he described it. So first he said, les électrons ne peuvent se placer que sous des orbitaux sécures d'énergie bien déterminée. So if you remember clearly, someone asked me a question. He asked me a question, which one is moving around? Is it the orbital or the electrons? I remember there was a misunderstanding. Instead of saying electrons, I said the orbital is the one moving around. So here, get me clearly. Here should get clear because I'm going to explain that. Here should get clearly. What is moving? So they're saying the electron ne peuvent se placer que sous the orbital sécure de énergie bien déterminée. So they said the electrons must be placed in orbital, which are what? Which are bien déterminé. So bien déterminé meaning the energy bien déterminé meaning the energy of this orbital here, the first orbital here, must be fixed. If I go to the energy here, the energy here must also be what? Fixed. And if I go to the energy here, the energy must be what? Fixed. So the energy is well precise according to Bohr. So I said the electrons must be in orbital, and this orbital must be precise, must have energy which are what? Determined. Then lors de son mouvement sous un orbital circulaire, l'électron est dans un état stationnaire. So here you should do, if you know that in the movement of an electron around this, so the one which is stationary here is the orbital is stationary, the electron is what is moving. So according to Bohr and according to, if you go deeper into mechanic classic, like mechanic classic, if you go deeper, if you start mechanic classic deeper, you understand that if something is moving in a stationary point, there's no loss of energy anyhow. Like there will be no loss of energy if it's a fixed orbital. If it is a fixed orbital, there's no loss of energy. Rather than if it's moving, you don't know if there's a fixed orbital or what. For Rutherford, he didn't explain or he didn't brought up about the fixed orbital. So for him, his problem was he didn't brought up about the fixed orbital, which means that an electron, when it is moving, according to mechanical classic, if there's no fixed orbital, it definitely loses energy. But if an electron is moving in a fixed orbital, there's no energy lost. So in solving this problem, Bohr said, actually, the electrons are not moving anyhow as my elder Rutherford said, but is actually there are some shells or there are some orbitals which are stationary, in which this electron is what is moving. So if they are stationary, meaning this electron, according to the mechanical classic, which we know, if it is moving in a stationary orbit, doesn't lose any energy. So that's one is placed in the electron is placed in shells which have what? It's placed in the shells with definite energies, meaning the energies are what? Are well determined, fixed, yeah, well determined. And when this electron is moving around this orbit, which is stationary, the electron doesn't lose any energy. This is what you should put in mind. So for Rutherford, there were no shells. For Bohr, he developed something like shells to help his brother. So the second one, which he discovered also, was that lorsque l'électron passait d'une orbitale stationnaire, this is orbital stationnaire, we said an orbital is stationary, to orbital, let's give this first orbital as M, orbital stationary, to an orbital stationary M. So N M. When it moves from there, there is an emission or absorption of energy, electromagnetic. So Bohr explained that this emission and absorption of energy is only done when this electron moves from one shell to another shell in simpler terms. Yeah, I can say in simpler terms, you can say when it moves from one shell to another shell, that's when it emits emission. But when it's moving in a stationary orbital, there's no energy lost. So yeah, so if it's moving in a fixed orbital, there's no energy lost. But when it moves from one shell to another shell, there'll be emission of what? Energy. So you only emit or absorb energy when you're moving from one step to another step. That's how Bohr explained it. Yeah. So what is absorption? So I'll try. What is absorption? So I'll try to explain absorption and emission. So absorption definitely is, assume an electron is here. Then there's energy which is coming in the form of photon. Photon, this is energy which comes from light. When it comes here, the electron here actually will absorb this energy and it will get excited. And when it gets excited, when you eat something like you get full, you start moving around. It's just the same thing as an electron. So an electron, when it gets excited, it will jump to the higher level shell. So there was a confusion here. There was another question which was asked here, and I want to precise this. Listen to me clearly. The question was, which shell has high energy, N1 or N2? That was the question which was asked. And this question, when I was answering it, I misplaced it with the force of attraction. So hear me clearly. So the one which has, when an electron absorbs energy, it goes to the outer shell, meaning it has, the outer shell is the one which is what? Which is higher energy. So the outer shell has higher energy than the inner shell. If we come to energy, since if it absorbs, it goes out. So the more an electron comes near to the nucleus, the middle part of the nucleus, the more the energy reduces, because when an electron comes near to the nucleus, it has to gain that state of stable, the stability. Yeah, the stability state, it has to get a state of stable. Then the opposite is, it has to get the stability, the state of stable. So, but you should also know that there's an opposite in such a way that you should also know this opposite. So we should also know this opposite. So when an electron gains an energy, so the outer shell has high energy, then according to attraction, you should listen to me clearly. According to the attraction, the one which is near to the nucleus is the one that has higher attraction. So if you see here, the shell N1 is near to the nucleus, so the attraction is higher for N1 rather than for N2. Then why is it higher? Because when you see here the radius, when the electrons moves to the outer shell, you see the radius from the outer shell to the nucleus is very, you can say long. It's very long. So when it's very, very long, it means the attraction also will reduce, but the distance from here to here is very short and the attraction is high. And again, should also know, for an electron to move for an electron to move from here to here, to absorb a photon energy, in form of what? Photon. And to move from here to here, it's emit what? Energy, meaning it loses energy. Energy what? Reduces. I don't know if it's clear from there.
It's clear.
It's clear.
Yeah.
Yeah. So we have seen all this. So he developed two postulates. One postulate: electrons are in fixed orbital in such a way that they are moving in fixed orbital, meaning they are not losing energy. And two, these electrons, they only emit energy or absorb energy when they move from one shell to another shell. You should bear this in mind. Yeah, these are things which will help you. So here we're not learning to memorize, but we are learning to know. If you know, you'll be able to, when you go to your universities, you won't have any difficulties in researching and doing what you already know. So I'm more concentrated on you knowing. So we have known this. So now we are going to go to this simple equation. Hello, you have got a question?
Yes. When an electron is excited and moves on to the next shell, is there a time when it might lose that energy it had obtained and return back to its normal shell? It continues orbiting around the next shell.
That's a nice question, actually. Yeah, when an electron is excited, it moves to another shell. What happens is a moment might come where it may lose that energy which it has observed, the photon energy, and which will make it to go back to the inner shell. So that's why I've said there's absorption and the emission. So it can absorb energy, it goes to another shell, then it moves maybe a bit. After moving, maybe it reaches a state of losing that energy, and then it goes back to its original shell. Clear?
It's clear.
Thank you. Yeah, so we'll continue with, Yeah, before we continue, I think there's a question somewhere. Okay. So the question was which shell has high energy? So the one which has high energy, since when an electron absorbs energy, it goes to the outer shell, meaning there's absorption, meaning it can gain more energy. So the outer shell has higher energy than the inner shell. Yeah, I hope I've explained that is clear. So without wasting any time.
I also have another question.
Mm-hmm.
For example, like in the noble gases, for example, those that have got those that are stable, and then maybe an electron is excited. So that means it's able to pass on to the next shell that has got eight electrons in its orbit.
That's a nice question, actually. I remember someone asking about that question. I remember someone asking about that question about an electron when it's, it's noble gas, stable. Yeah. And according to the octet law, where the octet rule, which you learned in Zambia, says that an electron, the outer shell must not surpass 8 electrons. So how do I answer that question? Yeah, I never even thought of that question. So I can say on this one, it is for all of us to research on this one. Yeah, I should research, and when we research on this one, we'll come to a conclusion. So you should research. Giving you a homework, actually, you should research on this one. What usually happens when an electron is stable, when an atom is stable? What usually happens when an atom is stable? When it absorbs energy. So you should search on this one. I hope it's clear.
Yes, it's clear.
Yeah, so research on this one, and if I come up with the answer, the next lesson when we come to learn, I'll come to explain to you guys. I'll also look into that. Yeah, you know, when you are having your semester, most of the times you don't overlook like the wider range. You just look where you are given. So I'll try to overlook and see what really happens, and I'll give you the response, inshallah, on Thursday. So we have EM minus EN. So now we're going to go to this simple formula. This simple formula. So what usually happens when energy is absorbed? So what usually happens when photon energy is absorbed? So when photon energy is absorbed, the electron moves from the energy level. This is simply means the energy level, or in a simpler term, it moves from the N shell to the M shell. So this is just the energy level, which is fixed. So this energy, EM minus EN, is equal to HV. So this is the formula for a photon, which is what? The formula for a photon, which is what? Absorbed. So a photon, like a photon energy, this is simply an energy from sun, and this energy, when an electron absorbs this energy, it makes its frequency to become high. And when the frequency, this is the frequency here. V, it is frequency, H is constant. So when the frequency comes high, it goes to what? To the outer shell. So here, the photon energy is always equated to Planck's constant, which is always, this Planck constant is always a constant which they have given you, which is H is equal to 6.626 times 10 to the power negative 34. Then V is the frequency. Yeah, frequency. Then you know that now how do you calculate, like, how do you calculate this energy? How can you relate this energy? How can you relate the energy which is absorbed to move it to the outer shell, or it is released to move it to the inner shell? How do you calculate it? So the first thing you have to put in mind is that you know that the formula for frequency is equal to, the formula for frequency is equal to acceleration, the speed of light, this is the speed of light, divided by longo dot. Longo dot is just the wavelength. I don't know if you still remember this formula from your secondary for frequency. So frequency is equal to speed of light over longo dot, and H is the constant of what? Planck. So how, like, now they just wanted to put this equation together. So where there's V, they just replace it by C over longo dot, which is C over wavelength. So the energy, this is the change of energy. The change of energy in such a way that it has changed. It has moved from the first shell to the second shell, or it has moved. Either it has moved from the first shell to the second shell, or the second shell to the first shell. That's the change of energy which we are talking about here. So the change of energy is equal to HC over longo dot. We just replace V here. So HC over longo dot. So with this formula, you'll be able to play with it. And this formula, like this is the major formula which we usually use to play with it to find the longo dot, to find the wavelength of the electron which has moved. What wavelength has the electron moved from N to N2? So you will find in your you understand it more when I give you questions and I tell you to find longo dot. So this one you have to know it by K. You have to know it by heart. You have to put it by heart, this equation. Yeah. Then there are some times where they can give you frequency. You can use this equation if they give you frequency. So it depends with what they have given you, and that's what you use. So now, this was the equation. So this brings us to, you know, all this, like all this which we have explained that in each shell, the energy is fixed. N1, the energy is fixed. N2, the energy is fixed, which brings us to quantification, du moment de la quantique de mouvement. So quantification du moment de la quantique de mouvement de l'électron, which simply means that at each shell, there's quantification. Quantification simply means the measurement, the quantity of something. The quantity of something, at each shell, there's a quantity of moment, or there's a measure of moment for the movement of what? This electron. And if you know this movement of moment, if you know this quantification of moment, you'll be able to understand now why an electron can move in a shell without losing what? In energy. So basically the equation which you want to, basically the equation, there's no need of you solving or what. The equation which you have to get by, by heart is this equation. So this is simply a simple equation. This is the movement of what? Let me try to explain it in this one. Yeah, let me try explaining it in this one. Where is it? There's something which I'm trying to do. Just wait a bit. Yeah, there's something which I'm trying to do. Yeah. Can you see it? Can you see my screen? Can you see my screen, my sharing?
Yes.
Okay. So I just want to facilitate. So this like which I'm explaining here, there's no need of you calculating. I just want you to show you why we say that when something is moving in a stationary orbit, it doesn't lose energy. So let's assume toujours we're going to be using hydrogen atom for this one. So let's assume this is an atom, this is a nucleus, this is an electron. So basically, moment is, so the r, this is the distance from the nucleus to the r is the distance between the nucleus and the electron. And the mv is the quantity of movement of an electron, the quantity of how an electron is moving. So this quantity you can denote just by p. So it's just denoted by p. So you should know that p represents mv. I hope it's clear. So how did they calculate it? I just want you to follow me. This one I'm just doing it fast, and we don't. Just want to show you how they concluded that there's no energy loss. So what they did is, you know that moment cinetic is equal to r. This means times p. Yeah. So p I said is mv, then r is the radius. So we see that I said p is equal to mv, then r is radius. So what he did first is he tried to differentiate it with a change of time. As we know that an electron, when it's moving, is moved in a constant change. Like when an electron is moving, each time is moving, time is also moving. So meaning when there's variation of moment, there's variation of time. So you try to do it by varying with a varying time. So dA over dt is equal to dr over dt times p. This is simply, you know, the differentiation of, if you are differentiating a product, you know, if you are differentiating something which is multiplying, you know how to differentiate. I hope, I don't know if those who did some ADMA, or even ordinary mathematics is there. So when you're differentiating, I said this is times. So I'm differentiating this one. So dA or dt, so when I differentiate, first I'll start differentiating dr over dt, P I want to differentiate times P plus R times dP now differentiate P, dP over dt. So we see according to how they explain, dr and dt, it represents the velocity, the vector of a velocity. And p, we know that it is mv. So we see that if there are two, we should know that if there are two vectors of velocities, vectors simply means velocity. When there are two velocity vectors are always opposite to each other. Yeah, they're always opposite to each other, which means that if there are two vectors, meaning they'll cancel each other, like it will be just like 0. So the whole, this one here, it will just give you a 0. Then dp and dt, they express it. They say this formula is used for what? For expressing what? Force exterior. So this thing, like I never really got into deep. I just got I want just to show you the general idea. So the force, the exterior force. So when they continue, they say that this one is 0. This one gives what? 0. And this one is R times the exterior force. This is R times the exterior force. Under system isolate, this is a system which does not change energy with it, which does not change matter and energy with the outside material, with the outside. So under system isolate, we know that the force exterior is always 0. This one is a principle which you should always know. It's always 0, which means that if force exterior is 0, meaning that when you multiply R times 0, it will give you, it will definitely give you 0. So it will show us that dL over dt is equal to 0. So L, the moment is equal to moment 0 here. So the L is 0. So we see that according to this equation. So it brought up this equation to just show them when an electron is moving. So I'm just trying to make up a build up. He brought that when an electron is moving around the shell, like for you, the most important thing you should know that when an electron is moving around the shell, there's no energy loss because it's moving at a what? Momentum. So for him to support his theory, he brought something like, he brought out a formula of momentum, or he brought out something new called quantification the momentum. So we'll just see that here we are only considering that this equation. So we just see this equation which our man Bohr brought in to explain to us more of why when an electron is moving in a orbital stationary is what doesn't lose any energy. So for this one, there's no need of what? There's no need of you knowing it. I wouldn't even advise you to go through it. But those who do mechanic du poids, you will learn about these things. I don't know if you have already learned about this. Yeah, but in chemistry, there's nothing like this. They just bring you direct to the answer. So I just wanted to enlighten your thinking so that you know why he brought quantification of moment. Yeah, so we'll continue. Yeah, so we'll continue. So we said he brought in the quantification of moment. This is the formula, MVR, where I said M, we see the quantity of movement, R is the radius between the electron and the nucleus, and NH, N is according to the shell. NH is the movement from one shell to another, then divided by 2 pi. 2 pi actually, if I wrote something here, down. When you see, like, I tried to bring 2 pi here, when you see this formula for 2 pi R, this simply means the circumference where the electron is moving. So he brought up this formula. So this is the formula which Bohr himself discovered. This is the formula of quantification du moment de la quantité de mouvement. Yeah, the electron. This is the formula which he discovered. So after discovering this formula, now we are going to see how he had put this formula now together with the formulas which Rutherford discovered. So he got the formulas which Rutherford already discovered, and he added his one formula which he discovered. For him to make his postulate true, he had to bring out one formula. So we see how this formula come about. So these things actually, there are things which are really simple, and as you go on further, we'll see when you find the energy total, actually they will even give us the what? The fixed value. You won't be using the formula, you won't be using, they'll give you the fixed value of that formula. So don't even worry, we'll be using this formula. No, you won't be using this formula. Yeah, so the only formula which you'll be using in calculation is this one and this one. Yeah. So continue. Yeah, so you know that applying the constant H represents the relation entre photon energy and the frequency. On multiply frequency H pour obtain photon energy. Yeah, I don't know if there's any question until now. If there's any question. So we know that the Planck constant H represents a relationship between a photon energy and a frequency. So we simply multiply frequency plus times constant times what? Constant the Planck for us to obtain this photon energy, which causes the electron to move to another shell. I don't know if there's any question until there. You can ask your question.
I wanted to find out what exactly it means when you say an electron is excited.
Oh, yeah. When an electron is excited, it simply means it has absorbed energy, some energy. When an electron is excited, it's absorbed energy in such a way that it can't stay in that same orbit which it is, in that same shell which it is, because the energy has increased. It will move to another shell so that it suits the energy of the energy which has increased, or this energy which has increased. So when it is excited, meaning it has absorbed something. Yeah, that's what it means. It has become excited. When you eat something, like for example, when you eat food, you will become energetic. You can do a lot of things. Yeah, that's the same thing with an electron. I don't know if it's clear.
It's clear.
Thank you very much. Any question? So now we'll go at it. How do you apply? How did he actually apply this equation which he found? The equation of what? So these are the equation which you know already, which we talked about. But here we just added one equation. This is the equation MVR is equal to NH over 2 pi. So this is the one equation which he added. So for him, he wanted to find the energy totality with this, the same equation which he added. So what did he do, or how did he do it so that how did he do it so that he includes this into the energy totality, and for him to be using this as his new formula for calculating energy totality? So you know that what he did is, so here is just a summary. When you add 1, 2, 3, it will give you negative EM to the power 4 over 8 epsilon power 2 h power 2 times 1 over n power 2 en. So now our en, where E0 is equal to negative ME4 to the power 4 over 8 epsilon to the power 2 H2. So now, how do you get this formula? So here I'm going just to talk how we get this formula. How did he arrive at this formula when he added his simple small equation? So what you should know just is he brought in this equation because he said electron moves in a constant orbital. That's what you should just put in mind. That's the most important thing. Yeah. So how did he do it? So the first thing is, first he checked under equation 1, equation 2, and equation 3. Which one has got MV and R? so that it is equation 3, which is the equation which you already know, which has mv, which is mv squared over r. This is force attraction, if you remember what we did. This is force Coulombian, if you remember what we did. So what did he do with this? So the first thing is he simplified it, r, which gave him mv squared, then which gave him over r. So what he did just here, it was supposed to be e squared over r, then he just did cross multiplication. So that's why you see the r going this side. Yeah, that's why you see the r going this side. So he just did cross multiplication. It was supposed to be e squared over r. Since when you divide here, you just remain with r. But for him, he multiplied. He did cross multiplication in such a way that the r moved the other side, which you have mv squared r. Now the problem is this one is so here we're trying to make it similar to this equation which is here. So you know that there is v squared, but there is no v squared here. How do you do with it? So how we did with it, how we solved it, he said, okay, I'll multiply by mr on both sides of the equation. So he multiplied here with mr, which gave him mr e squared over 4 pi epsilon is equal to mr squared mv squared r squared. So when he got this, he said, now it's possible for me to express it in terms of this one, because I'll just what? I'll just factorize it. When I factorize it, I'll just have mvr brackets. It's same if I write mvr brackets to the power 2. It's just similar. There's no difference. mvr brackets to the power 2, which is equal to mvr squared over, I'm just saying this one, mvr squared over 4 pi epsilon 0, which is equal to this one, this equation here. Since I'll put this one in to the power 2, meaning this one I also put it in brackets to the power 2 so that it becomes equal. So I'll put it in brackets to the power 2. So which will give me, which will be equals to mr e squared over 4 pi e0 times, you know, if it is 2, meaning it will be n2 h2 divided by 4 pi 2. If I multiply, if I try multiplying everything inside here, this is the same thing here. So when I bring it that I can say when I want to multiply it, when I bring it to the other side here, when I'm multiplying it, it means the one which is down must move on top. You know, this is a simple mathematics. One which is down will move on top, and the one which is on top will move down. That's how the equation is. So he multiplied this together. So after multiplying this together, it gave him something like m squared pi over epsilon 0 h squared times 1 over n squared. That's what it gave him. Then this is the energy total. This is, you know, the energy total. This is the energy which we have here already. The energy total here, which we have here. Yeah, this is the energy total which we found the perfect. That's what I'm saying. It was very important for you to know the energy total. So when you write this energy total actually it was supposed to be e squared over r, but seeing that there was r here, that's what I'm saying. You are seeing r that disappeared here because it cancelled. There was supposed to be over r, it cancelled, r, it cancelled. So the r cancelled. That's why we are just remaining with negative 1 over 8 pi epsilon times e squared times me squared epsilon over e0 a squared times, this is just the same as n2 divided by n2, just the same. I put it just aside 1 over n2, so there's nothing complicated here. Yeah. Which will give us our final equation where energy total is equal to negative m, which is the mass of an electron, charge of an electron e to the power 4 over 8 epsilon to the power 2 h2 times 1 over n2, which is this whole formula is just equal to E0. So En is equal to E0 over N2, which is a fixed. So there's no need of you Kuswatilisation formula. There's no need of you memorizing this formula. They are already calculated for you, which is negative 13.6. This is the formula which you'll be using when calculating. You won't be using this formula. So there's no need. That's why I was moving very fast in such a way that I know that this is the formula which you'll be using to calculate when you want to find the energy in each shell. This is the formula which you'll be using. There, I see there's a hand. Yeah, there was a question which said E0. E0 simply means E0 represents this whole thing, this whole thing. It is E0. That's what we are seeing it. This whole thing is E0. So this whole thing is something which was calculated, which is something which is what? Constant. Something which was already calculated, which is negative 13.6 over N2. So if you want, if I say the first energy shell, you can try on your calculators to calculate the first energy shell. The first energy shell, to calculate its energy, you just use negative 13.6 over N2. Then if N is 1, then you find that the first shell its energy is negative 13.6. If N is 2, you just divide negative 13.6 by 2, you find this energy. So you go like that. That's how, if you're finding energy in one shell. Then if an electron has moved from one shell to another shell, for example, what example can I give? Yeah. So when it has moved, for example, just imagine the shells which we saw there, the shells when I was talking about absorption and emission. When you absorb an electron, it moves from let's assume those shells there's N and M. N is the inner shell. Yeah, just be thinking like that. N is inner shell, then M is the outer shell. Assume like that. So the electron has moved from N to M. So how do you calculate the energy of that movement from N to M? This is the formula here, the second formula here. This is the formula which you use. So for you to calculate the energy, the movement, to calculate this movement of energy, here actually was supposed to be delta A. It was supposed to be delta A showing not energy N. Yeah, I'll try changing, then I'll send you another PDF. It was supposed to be delta A, meaning they are changing from one energy. So these N and M are different energy shells, or they are different shells. So they are changing. So how do you calculate it? So you calculate it. This is the final shell where it reaches. The N is the final shell where it reaches. Then the M is the initial shell where it is coming from. So it can be interchangeable. If I'm doing emission, where I'm starting from is the inner shell. So my M will be inner shell, then my N will be the outer shell. Or in simpler terms, where you are ending must be the first part. And where you are starting must always be the first part. So emission you are starting from the outer shell going to the inner shell. So the outer shell will be the outer part, the inner shell will be you are starting from the outer shell going to the inner shell. So the inner shell will be the N2, sorry. Then the outer shell will be the M2, where you are starting from. So where you're starting from is always Kumbari, then yeah. So that's the energy. So they will tell you, calculate the energy. The atom moved from N1 to M2. The electron moved from N1 to N2. With this calculate this energy, you'll be able to calculate this energy. Or they'll tell you that the energy, the change of energy when the electron moved from N1 to N2 is this. Calculate this one. Yeah, so those are the things. Those are the things which you face mostly. Yeah. I don't know if it's clear or I should repeat.
I have a question.
So, yeah, you can ask your question.
Yes.
So you understand this more when after this I'll give you some questions where you should answer and you will understand it more. Yeah, you can answer your question, bosses.
Yes, you are from saying N and M. These are different shells, right? Now, what
Yeah.
are we going to replace there on N and M? Is it the distance from the nucleus to that same first shell, second shell, just like that?
No. N you replace if it is shell number 1. If they say it is shell number 1, you replace by 1. So it will be 1 squared. It goes to the shell number 2. Since the shells, the shell number 1, which is near to the nucleus, the shell number 2, the shell number 3, that's how it goes. So if it is shell number 1, it will be 1. If it goes to shell number 2, it will be, so N will be, for example, it has moved from shell number 1 to shell number 2. So N it will be 2 squared minus 1 over M it will be, since it has come from 1, it will be 1 squared. I don't know if it's clear.
Yes, it's clear.
Then if they just tell you calculate the energy in one shell, like they haven't told you that it has moved from this and this. No, they say calculate the energy in one shell. You just use this formula direct. You just divide by, you just check it is shell number what? Okay, shell number 1. Okay, I'll just divide 1 by what to find the energy of that shell. Or shell number what? Number 2. I'll just divide 2 by say negative 13.6. I'll find this energy. That's how you go about it. So when question usually comes, you should always be checking. There'll be these people when they're asking questions, they are very, very clever. They'll put emission and the absorption. So you have to know what emission means and what absorption means. So when you see in your question, you read your question, you see there's emission. Now it moves from one stage to another by emitting or by emitting what? Then you know that it moves from a higher level to a lower level, to a higher energy level, or to the higher shell to a lower shell. Then if they say it absorbed, then you know that it moved from the lower shell to higher shell. So when they give you your end, like by just the statement, you know that it is moving from lower shell to higher shell. Sometimes they ask you, find the energy level. So you have to find the N, find the N. So they give you the energy, then they tell you find the N. You have to know, is it emission? So you will always look for this question, for this word, emission, absorption, emission, absorption. When you are posed with this, when you're posed with the questions like this. So I'll send questions for you guys so that you understand it more. And when you solve questions, you understand, you will really understand it. Then there's also Raymond the atom. You get the Raymond the atom. This one just need to know the formula so they can ask you calculate the Raymond the atom, the Bohr. They ask this question also. So you just have to put just the formula by heart. There's no need of even deriving it. There's no need of deriving it. Yeah, it can take a lot of time because this one they just like you just solve it directly. Yeah, so there's no need of deriving it. So Raymond the atom is simply the radius. When I say Raymond the atom, meaning the radius of Bohr from the nucleus. No, it's the radius of the atom in general. Yeah, the radius of an atom in general. You can say the radius from the nucleus to the electron. So that's the Raymond the Bohr. So most of the time they say calculate the Raymond the atom the Bohr. So this is the formula which you should use. Rn is equal to R0 times n squared. So I've said n is always the shells. If it is in the first shell, it is in the second shell, it is in the third shell. Yeah, so that's what to determine. Then A0 is always a constant. You should put this in what? You should memorize this constant, which is always a constant. A0 is always a constant. So it will be Rn is equal to this constant times N2. So the only thing which you should know just is the shell. In which shell are you in? The electron is in which shell? That's the only thing which you have to know. So you have seen these things, the calculations, the derivation, those things are just bringing us to something which is very simple and something which is giving us a constant, and which is negative 13.6. And here it will be just like, I give you everything already, like you have been given everything already. You just need to know this shell is in which electron, or this shell has moved from what electron to what electron. Those are the things which you are only supposed to know. Yeah, then if you know those things, if you come to understand those things, you will never fail any question under Bohr. You'll be always getting every question. So when you do some questions, you even understand it more. So A0 est appelé royaume de l'atome de Bohr. That's what it is called. Then le modèle de Bohr montre que l'énergie de l'atome de hydrogène ne prend que des values bien définies. So it shows that each orbital has a value of energy which is fixed, which is quantified, in other words, which is already measured, if I can say so, which is already measured. So this energy will be always what? Constant. So if you see the first energy, if you try, someone who has a calculator, if you have a calculator near you, you can try the first energy, the first shell, you find your n, using that formula, negative 13.6 over n squared. So you find, you find that your first one, it will give you 13.6, the same one, 13.6, will give you negative 13.6. I forgot negative 13.6. Then the second one, it will give you negative 3.4. If you check it, if you try the division, that's what it will. The second shell, that's what it will give you. Yeah, that's if you try on your calculator, that's how it is. So he said the energies are always quantified, are always measured in each shell. They're always constant in each shell. Yeah, they're always constant. So the only energy which we are calculating, you should get me clear. The only energy which you are calculating is the energy which was absorbed for it to move to the another shell. But if you want to calculate the energy of each shell, you'll find it is constant. But the energy of it moving from one shell to another is changing depending if it has moved from N1. It can move from the first shell to the third shell, or it can move from the first shell to the second shell, or it can move from the third shell to the first shell, the third shell to the second shell. It depends on how the question is given to you. So yeah, so you can use, so the one last thing. Yeah, one last thing. We don't even have time, or the time is over. So one last thing, you can use this formula to find energy. Then when you have found your energy, there's this formula which I want you to know. You can use this formula after finding your energy. You can use this formula to find longitude, like the wavelength. There are some times where they ask you to find the wavelength. So you just use what? This formula. So you know your energy, which you have found using that formula, which we are from doing. After you have found your energy, then you just use this formula, the longitude here. Just use it. You just make the longitude the subject to the formula. So it will be longitude is equal to hc over change in energy, which you have already found the change in energy. So you find your longitude. Yeah. So for today, we don't have enough time. I hope everything is clear, the things which I've explained.
It's clear.
Yeah, so don't forget the homework which I've given you. You should change. You should search for what happens when you have an atom which is stable. What happens in terms of absorption and emission? So I need some answers. Yeah, I need some answers. Before Thursday, I'm expecting some answers. Yeah. Then I'll give you some exercise. Yeah, today I'll give you some exercise on these things, how to calculate the energy, how to calculate load, all that. I'll give you some exercises. We see how you fare, and yeah, we'll be correcting each other. From there, that's how you learn. You have some ideas, and I know you won't even have any difficulties when you go to your universities. Yeah. So for today, I say thank you. That's all, and have a blessed day. Yeah, it was really an amazing lesson. Yeah, and next time we'll continue. So next time we'll continue on. We'll now look at something which is very interesting. We'll look at the series. After we look at the series, Yeah, those are the things which we look at. Bauma, those all things. Yeah, that's what we look at. Yeah. So for today, thank you and have a blessed day. Yeah, I was supposed to give you something like homework or something, but I think I'll give you on Thursday. There's something which I want you to do a research, so you can do it on a weekend. There's a certain topic which I want you to do a research on, so I'll give you on Thursday. Since seeing that we don't have enough time, and I'm moving in such a way that I want you guys to understand. So yeah, so some things I'll be giving you as a task to do. Then when you do them, those who send me answers, I'll be explaining how to do them. Then they'll get the knowledge after getting the knowledge, as long as they have an idea.
Do suspect personal loyalty.